In the last module, we were discussing critical heat flux and the mechanisms that are needed or that control CHF. The two mechanisms that are responsible for CHF are dry out and departure from nucleate boiling. We saw how heat flux control situation was analyzed. We also quickly saw how wall temperature control situation was going to be analyzed. In this module, we will conclude this wall temperature control situation and also go through certain aspects of film boiling heat transfer and complete this discussion on boiling curve. So, in the last module, I have just taken the slide from the previous module. We had stopped somewhere here and we said that this was saturated nucleate boiling region. I progressively increase the wall temperature. I will reach a situation where the wall temperature becomes that little bit more than what it can sustain for good nucleation, and after that you would see alternate random contact of the liquid with the heated surface. By that I mean, if I take the top view of this vessel or wherever this thing is happening, at say this value of T wall, let us say this one. So, let me call this A, I will give another example at B and C, so on and so forth. At location A, probably you would see a few dry spots, or you would have a local, you will have a condition where you do not have liquid contact at a particular point. Then at location B, where the wall temperature is further increased, certain other locations, maybe these two locations, start to become inactive or inaccessible to the liquid. Further increase in wall temperature, you would start to see several locations on the heated surface where liquid will not be able to come in contact with the heated surface. This situation finally becomes worse when I go to this temperature of T wall equal to T Leidenfrost, or we call this Leidenfrost temperature or minimum film boiling temperature. This is given the term T min, minimum film boiling temperature. What it represents is that temperature at which the liquid can be in contact with the heated surface. Any further increase in the wall temperature will result in the liquid losing contact with the heated surface permanently. And what you would see in this wall temperature control experiment is, if I progressively increase the wall temperature beyond this, that means I go from here to the right, what would happen is immediately you would see an excursion in the boiling curve this way. Further increase, you would go to a higher heat flux. You might be wondering why this is happening. Oh, I am having a higher heat flux for a small increase in wall temperature, it is good. What it means is it is better than what it was here. In this portion, the transition boiling actually is really bad. In film boiling, what you get is the slope is parallel to what you have in the nucleate boiling, except that the delta x's are really large because we are in a log-log curve. In film boiling, this region is called as film boiling. What happens here is that for a small increase in wall temperature, remember you are talking of temperatures of the order of few hundreds or even thousands of degrees. So, mechanism of heat transfer is no longer pure convection or change of phase, you have radiation which becomes dominant. Radiation becomes very important. You have sensible heat transfer to the vapor, you have sensible heat transfer to the liquid which is there beyond the film in case of a DNV situation. Remember, here you have vapor here and liquid here. So, radiation from here to this surface and then to the liquid is also possible, and therefore, the heat transfer coefficient in film boiling is slightly higher. Nevertheless, it is not a good thing, because it is very bad to have such low heat transfer coefficient and high heat flux on surfaces for extended period of time, because that will cause complete degradation of the surface, and that phenomena or that situation where there is a physical destruction of the surface is called as burnout. Burnout dry out, DNB, CHF. These are all terms which are used interchangeably by many people. So, CHF we have dry out, we have DNB, and we have burn out. These are 4 different things which are used interchangeably by people. Unfortunately, we will just try to get a perspective on what each of these is. A dry out, we said, where no liquid exists to cause change of phase. Nice. So, you do not have any more inventory, therefore, we have a situation called as dry out. The surface is dry. DNB, liquid exists but unable reach heater surface, therefore no nucleation possible. This is called as departure, moving away, departure from nucleate boiling. These two are good. These two represent the mechanisms of by which heat transfer coefficient suddenly drops. Q-wall controlled case, what do you see? How is this heat transfer coefficient drop manifesting itself? You see this as a TW increase. In TW controlled case, you see this as a reduction in the heat flux. Remember this? You saw this as a reduction in the heat flux. Manifestation of decrease in the heat transfer coefficient is seen by you as a decrease in the heat flux. These are mechanisms of reduction in heat transfer coefficient. That situation where such a thing happens, this whole family of things is grouped under what is conventionally known as CHF, or for lack of a better term, it is that point where good heat transfer characteristics end. That is the way you should remember this. So, the point on the boiling curve where you go to this maximum point and afterwards either you could do this or you could go directly here. This point is so called CHF point. We also understood that the CHF point is directly not a constant. You could have different situations where CHF could occur for different values of heat flux and wall temperature. So, as we said, it is not a number that you will find in a textbook or which is tabulated. You have what we call as CHF lookup tables for different geometries and different experimental conditions of pipe diameter, pressure, inlet subcooling, length, so on and so forth. So, it is a huge collection of data which is available as CHF data, and you go and look up for those values of CHF for a particular experimental condition. If you do not have that, you are using a different fluid in say same diameter 1-inch pipe under the same condition, but there is no data available. You have to conduct experiments for CHF and then get the values of the heat flux. That goes for critical heat flux values. What is burnout? Burnout refers to the physical destruction of the surface. So, you would have been told, the immersion heater that you would use for getting hot water, if the water is not there, or sometimes you would just turn on the plug, turn on the power without having water in the bucket, what would happen is the coil would completely get short and you would have physical destruction of the surface. This is because there is no sink for the heat to be removed. Physical destruction of the surface. This is a result. This is nothing. This is not a phenomena. This is a result of prolonged situations of high T wall and low QW. So, this, if you keep any heated surface like this for a long time, you would go to a physical destruction or a burnout of this surface. So, these are the 4 terms which are used many times by people interchangeably. Now, we will just go back to the wall temperature control case. When the wall temperature is increased beyond this point of minimum film boiling temperature, you would go to what is called as film boiling. I will explain the characteristics of film boiling in a little bit. So, I continue to increase the wall temperature, I would go in this manner. If I decrease the wall temperature, as we did in this case where I decrease the heat flux, when I decrease the heat flux, I came along this path and then went here. In case of wall temperature control case, I would follow the same curve with a small hysteresis, but the kind of data that you get for transition boiling, you get very little data, wide scatter, because what is the temperature that you would measure, because you have several spots which are dry, several spots which are wet, and the frequency of one spot being wet versus dry, etc., keeps on changing. It's so much randomness there. So, the entire data is very scattered and you do not get lot of data points also. So, you would see this hysteresis there in the boiling curve, in the transition boiling. Apart from that, the nature of the boiling curve is exactly the same. So, if I combine these two curves, if I combine these two boiling curves and show one boiling curve, what you see in the textbook is the following. You have wall heat flux, T wall minus T sat here, Q double prime here, single phase natural convection, partial nucleate boiling, saturated nucleate boiling, and this is what most books will show you. So, this is the good heat transfer part, this is your so called CHF. You know now it is not a mechanism, it is a manifestation of two different types of mechanism, either of which could be there. This is called as transition boiling and this is called as film boiling. This is Leidenfrost temperature or T min, Leidenfrost point. Your boiling curve would be this purple one, or you could go along this way, go along this way and come back this way. The black represents the heat flux controlled case and the blue represents the wall temperature controlled case. What is film boiling? Film boiling is a broad term where you are talking about a case where a film of vapor is surrounding the heated surface. So, this is the heated surface, this could be a wire or a plate or a pan, whatever it may be. You have a heated surface which is completely enveloped by a film. This film could be continuous, this film could be local, it could have varying thicknesses, so on and so forth. Does not matter what it is, what we are trying to say is there is a vapor film which is going to cover the heated surface, prevent good heat transfer because of its poor thermal conductivity. When the liquid exists here, the cause is basically DNB. If there is no liquid, there is no question of any particular film, it is just vapor. So, you have the vapor of the liquid. This is the vapor phase and this is the heated surface. So, when you have a situation where you have gotten to CHF because of DNB, you would be in this situation. When you are in a situation of CHF because of dry out, no more liquid is there, you will be in this situation. Point being, both of them result in the same problems, that there is no sink for good heat transfer to occur, and because of this you have, this becomes little easier to analyze, this becomes a little difficult to analyze because you have multiple paths for heat transfer, multiple paths being you have sensible heating of the liquid, sensible heating of the vapor, some amount of liquid gets converted to vapor at the interface. So, there has to be a budget for that also. how much is going to get converted would dictate the growth of the film. So, budgeting of this Q double prime into sensible heating of liquid, sensible heating of vapor, radiation to interface. This can be treated as heat transfer between two parallel cylinders. Then you have conversion of liquid to vapor. These multiple mechanisms are going to be there in film boiling. So, for us to model film boiling is going to become very difficult. It is a poor heat transfer mechanism, you do not like it, we should not have any device, any equipment work in film boiling mode, because your wall temperatures are going to remain high for an extended period of time. That is not good from the point of view of safety, and therefore, whenever you have film boiling, you would like to get it back to nucleate boiling as quickly as possible. Nevertheless, you might encounter situations where film boiling is there. Modeling of this becomes very difficult, radiation becomes very important. You cannot neglect radiation, this may contribute up to 40% of the heat transfer here, and all said and done, even though this region is not so good in terms of the heat transfer, from a point of view of fundamental studies in boiling in multi-phase flow, this regime helps us understand several things, and several challenging problems can be there in this modeling of film boiling. Now, we saw two different mechanisms of CHF, right. In both of these manifests itself as a reduction in heat transfer coefficient. Okay. In which is the situation more sudden? When you have DNB, DNB occurs without any warning. DNB is so sudden. Okay. If I have a pipe in which you are trying to see what is happening. So, the same thing what we did for a pool can be done for a flow. Okay. I will just talk about that in a minute. See, this is called as a pool boiling curve. For whatever reason, this is called as a pool boiling curve. Now, you might ask me, okay, you have a pool boiling curve, there should be a flow boiling curve. No, there is nothing like a flow boiling curve. The nature of the curve is similar, except that the heat transfer coefficient for flow boiling would be slightly greater than the heat transfer coefficient for a pool boiling situation, because of the additional force convection effect that is there. This force convection effect that is present increases the value of H in flow boiling. This is what changes the magnitude. So, you have a nucleation part and you have a force convection part. The force convection part is the extra thing that is there. So, the nature of the curve would be similar, except that the slopes would be slightly different. So, you would have a boiling curve whose slope probably does this, and you would get something like this. Okay. I am not going to crowd this picture for that, but the point being, both pool boiling as well as flow boiling curves would be similar in nature. The magnitude of the heat transfer coefficient would be higher for flow boiling than for pool boiling. Now, whatever we did for a pool, the same thing is valid for a flow through a pipe, which is a very classical geometry in boiling in industries for evaporator, steam generator, condenser, so on and so forth. So, if I take the case of a pipe through which things are flowing, we did this energy balance last time also. What we need to understand here is, if we take a constant heat flux situation, the result and the interpretations will be similar for wall temperature control case. So, here we have a constant heat flux situation, say Q double prime pi d dz is equal to dx into m dot into hfg, and therefore, dx by dz is equal to Q double prime pi d by m dot hfg, and this on integration would give you x of z is equal to x of I plus Q double prime pi d z by m dot hfg. We have seen this energy balance before with several assumptions. So, my quality at constant wall heat flux situation will linearly increase because this is a straight line relationship. And what you would see, void fraction or alpha is a function of properties rho f, rho g, thermodynamic quality uf ug, and we saw the relationship last time. It's going to be 1 over 1 plus rho g by rho f ug by uf, sorry, m dot g by m dot f plus m dot g. This is nothing but 1 over rho f by rho g, af by ag, uf by ug plus 1, that is nothing but 1 over rho f by rho g, af by ag we saw was 1 minus alpha by alpha, this is 1 over slip ratio plus 1. So, x and alpha have a non-linear relationship and alpha will vary according to this situation. Okay. Now, what happens is that when we discussed the introduction to boiling, we said that the nature of the flow pattern dictates how the heat transfer is occurring. So, we will quickly say you have initially when you have liquid coming in, if this pipe is very long, we do not worry about the length, and if the liquid is coming in as subcooled liquid, you would have a single phase region in the subcooled part, then you have a two phase part here. Subcooled part, your energy balance will be pi q double prime pi d dz is equal to m dot delta h or m dot cp delta t. It will show an increase in wall temperature and the fluid temperature, and these things also we have seen. This is how the wall temperature will be, T bulk mean of Z, T wall temperature as a function of Z. This all we have seen before, and this is T versus flow direction, this is your Z. Okay. Now, when you are in the two phase part, you would be in what we call as bubbly flow here, and so on and so forth, and very quickly the flow will go to what we call as annular flow. Annular flow represents the situation where you have vapor in the core and liquid at the wall. This is unlike film boiling, where you had vapor in contact with the heated surface and liquid away from it. So, we are talking of good heat transfer. So, when you are in nucleate boiling, when you are in this part, the pattern or the regimes of the flow would be bubbly, slug, so on and so forth. Bubbly is where a lot of bubbles are there, slug is where all the bubbles come together and form a large single bubble, and afterwards when the velocities of the liquid phase and the gas phase become vastly different, it is as if the gas phase is going to flow like a bullet through the pipe. So, you might be in a railway station where a super fast train is going by a platform, and there is an announcement that you are supposed to move away from the edge of the platform. So, the flow of vapor is akin that only. So, when the vapor flows through through a liquid phase, the vapor accelerates and pushes the liquid to the sides. This pushing of the liquid to the sides of a slow moving fluid is pushed to the side and the rapidly moving fluid goes through the center, gives a flow situation which is called as a annular flow. Annular flow is conventionally represented like this. Annulus, that is why annular flow. This is the thickness of the liquid film. This is not constant. This is not constant even as a function of theta. So, it could be any particular thickness at any location. It could change, it is going to change with flow direction. As I move from location Z1 to another location Z2, I am generating more and more vapor, and the liquid film therefore will become thinner and thinner. Finally, in case of dry out, the liquid film will eventually be gone. This situation is what we call as dry out, where there is no more liquid. But remember, the flow is extremely chaotic, turbulent. So, you have most of the two phase flow situations would be turbulent, random. So, the liquid and the vapor film interface will be very wavy interface, nothing will be smooth here. There will be liquid which is sheared as droplets, ligaments, etc. here. So, there will be large liquid droplets and those would get sheared because of the difference in the velocities of the liquid and the vapor, and what you would see eventually is small droplets, and finally if I go ahead I would get to see very small droplets, and finally no more droplets present. So, if I am talking of a situation where I have a pipe which is very long, I do not care about the length of the pipe, and this thought experiment is proceeding. Dry out will represent a situation where there is liquid in the core, but not in the form of a liquid at the wall is lost, but there is liquid in the core in the form of droplets or fine droplets or slightly large droplet, does not matter what they are. The point being, you have a sink for heat here. So, when there is a liquid, the heat transfer coefficient is good. Evaporation, or if this is a large droplet, when it evaporates it becomes a smaller droplets. Evaporation is a surface phenomena. 4 pi r square is the surface area of a sphere. So, there is a nice surface area through which evaporation occurs. So, H can be reasonably good in case of a dry out, where because of these droplets which are present, though the droplet size will decrease, you have a sink for the heat, and therefore, what I wanted to tell you here is, in case of CHF because of dry out, CHF because of dry out, decrease in the heat transfer coefficient, H reduction is smaller. I am not saying it is not there, it is very much there. It is smaller compared to H reduction in DNB. Why is that so? In DNB, you do not have DNB, no sink for heat, because vapor provides an insulating blanket. Vapor provides an insulation blanket. So, you have liquid, lot of liquid is there, and this vapor is like an insulating blanket. It does not allow the heat to go, and because it does not allow the heat to go, the reduction in heat transfer coefficient H drop, H before is much larger than H after CHF has occurred. Whereas, in case of dry out, H after is, I am just putting 2 less than sign, whereas here it was 3 less than sign, H before. The reduction in the heat transfer coefficient is there in both cases. However, in this case the reduction in the heat transfer coefficient is smaller compared to DNB, because this happens because of a formation of vapor film. This is very sudden, it can happen momentarily, whereas here you get enough time to take corrective action. You know that somewhere here is going to have dry out happening. So, if you reduce the heat flux, you may prolong the location of dry out, or you may extend the location of the dry out almost to the end of the pipe. You may prolong the two phase region to the end of the pipe. So, this comes with a lot of warning. Dry out is not sudden, can be predicted. This is sudden, very difficult to predict. H drop, very severe. H drop, less severe. Why? Because I have sink in the form of liquid droplets which are going to evaporate and carry away the heat. So, until I reach complete vapor, so this could be x is equal to 0.92 or something where this happens. So, till I go to x equal to 100 or x equal to 100% quality, I have a sink where heat is going to be removed, and therefore, drop in heat transfer coefficient would be less severe. Damage or wall temperature rise is lesser. Here wall temperature rise is much greater. Okay. So, with this we will come to the end of the module related to boiling heat transfer. This was just given as a primer for many of us to understand, because most undergraduate institutions have an experimental setup to talk about boiling. So, it would be good to explain these things to the students. Most of the experiment would be with a wire which supplies the heat to a pool. So, CHF, DNB, dry out, All these things are very different. Through this module, we have tried to explain what a boiling curve is, what are the different regimes of the boiling curve, tried to understand difference between dry out and DNB, which are both mechanisms of CHF, talk a little about nucleate boiling, talk a little about film boiling, and also define terms like Leidenfrost point, minimum film boiling temperature, differences between the mechanisms that are there for dry out and DNB. Thank you.